Hello students, I am Sachitrakar. Welcome to Cars Physics. We are continuing moving charge and magnetism. In previous lectures we have discussed motion of a charged particle in a uniform magnetic field, and of course we have discussed force on a current carrying conductor placed in a uniform magnetic field. Okay, and of course we have discussed force experienced by a charged particle moving in a magnetic field, and in previous studies, means in electrostatics, we have discussed what is force experienced by a charged particle in an uniform electric field. Okay, and finally in this chapter, means in moving charge and magnetism, we have discussed motion of charged particle in combined electric and magnetic field. Okay, and in that case the resultant force experienced by the charged particle is due to vector sum of force experienced by the charged particle in electric field and force experienced by charged particle in the magnetic field. Okay, and that resultant force, means force experienced by the charged particle in combined electric and magnetic field, is called as Lorentz force. Okay, so it will be very clear that why I am discussing about force on charged particle. Okay, in this lecture we will discuss on velocity filter. Okay, of course velocity filter is also called as velocity selector or Wien filter. Okay, velocity filter is also called as velocity selector or Wien filter. Then what is a velocity filter? The fundamental definition I have written. So, velocity filter is like a radioactive source. Okay, and it is designed so that, or it is so designed that it selects a charged particle or selects charged particles. It is so designed that it selects charged particles moving with a particular velocity from a number of charges moving with different velocities. This is the basic concept of velocity selector or velocity filter. So, velocity filter selects those charged particles which move with a given velocity or with a specified velocity from a number of charges moving with different velocities. Means our discussion clears that why it is called as velocity filter or velocity selector. Okay, it filters the charges and it selects those charges moving with a particular velocity. Velocity selector, it selects particular charges, and again we are writing velocity select filter, means it filters and allows those charges which move with a particular velocity. Okay, then principle on which velocity filter or velocity selector works. Principle is it uses the effect of Lorentz force. And we know, we have already discussed resultant force experienced by the charged particle moving in combined electric field and magnetic field is called as Lorentz force. So, velocity selector works by using the principle of Lorentz force. Okay. Then let's discuss about the various factors in velocity field. Okay. Suppose we are considering an uniform electric field. An uniform electric field. See, electric field is uniform as we have discussed. Electric field or magnetic field, whatever may. The field is uniform. If field lines are parallel and equidistant, you just imagine this is the direction of electric field. And I have represented an uniform electric field in this space, directed in upward direction. Suppose this is a charged particle plus Q. You may take alpha particle or charged ions, positively charged ions or charged particle. Okay. Suppose this charged particle is projected into the electric field with a velocity v such that angle between velocity of charged particle and electric field is 90 degree. Here velocity is in this direction. Say this is along positive x-axis and electric field is represented along y-axis. So obviously angle between velocity and electric field is 90 degree. As we have discussed, in this case the charged particle will follow. See, this is positive charge. This is positive charge and direction of electric field is in upward direction. So this positive charge particle is repelled by electric field along the direction of field. Okay. So force experienced by the charge particle will be in upward direction and that force is equal to QE. Positively charged particle experiences a force along the direction of electric field and magnitude of force is QE and direction is along the direction of electric field. See, velocity is along this direction. Okay. Force is along this direction means perpendicular to velocity. Obviously, it will change the direction of velocity without changing magnitude of velocity, since force is perpendicular to velocity. And we have discussed in brief in electrostatics. In electrostatics, we have discussed in brief motion of charged particle in uniform electric field. I hope you have gone through the lecture. So, as we have discussed, if a charged particle moves in a electric field, means if a charged particle projected to the electric field at an angle 90 degree, it will follow a parabolic path. So, nature of trajectory is parabolic or path is parabolic. The charge moves in a parabolic path. Okay. Next. Let's represent, this is first case, representation of electric field, and let's represent an uniform magnetic field. I am taking dot field, you may take also cross field. Okay. This is the representation of uniform magnetic field, dot field. Okay. Then if I represent the dot field, here direction of magnetic field is in outward direction. Direction of magnetic field is in outward direction. This is the direction of magnetic field. Okay. Suppose now a positively charged particle is projected into the field with a velocity v. Here also, angle between magnetic field and velocity is 90 degree. See, magnetic field is in outward direction and velocity is parallel to this plane. Magnetic field is perpendicular to the plane. And here again, angle between velocity and magnetic field is 90 degree. And as we have discussed just in previous lectures, if a charged particle is projected at an angle 90 degree to the magnetic field, then it follows a circular path. Okay. Then what is direction of force experienced by the charged particle? Then, as you know, force experienced by the charged particle is equal to Q into V cross V. So, in this case, angle between V and V is 90 degree and direction of force is along the direction of V cross V. In simplest way, this is the direction of velocity, this is the direction of velocity and this is direction of magnetic field. So, V cross V, V cross V, this is the direction of magnetic field outward and this is direction of velocity. So, V cross V, V cross V. So, direction of force is in downward direction. So, now force on this particle is in downward direction and here magnitude of force is equal to QVB. V cross V, VB sin theta and here magnitude of force is QVB sin 90 and this is force experienced by the charged particle. Again we know, if a charged particle projected perpendicular to the direction of magnetic field, it experiences a force and the nature of trajectory is circular. Thus, the charged particle will tend to move in a circular path. If everywhere there is magnetic field, then it will complete a circular path. Okay. Suppose I am changing the representation. Okay. Suppose I am returning to the previous diagram. This is representation of uniform electric field. Uniform electric field E in upward direction and in this region electric field is present. In this region electric field is present. Okay. Suppose this is an opening. In this opening a number of charges are allowed to flow into the electric field. And what we have discussed, suppose we are considering a positive charge plus Q and here we are provided a small exit path means window. This is an window. So, charge particle is projected in this direction with a velocity v and force experienced by the charge particle is F. Force experienced by the charge particle is F and here the charge particle will follow a parabolic path and will strike on this surface Thus it will not move through the window. Okay. Number one. And again, if you represent the uniform magnetic field, in outward direction means a dot field in outward direction. Okay. Again the same condition. This is an entrance. A number of charged particles are entering through this entrance. Okay. Let's consider a positively charged particle plus Q. Velocity given to the charged particle is V and magnetic field is in outward direction. Then V cross V force is in downward direction. So this force, as we have discussed, is QVB. Magnitude of force is QVB. So as we have discussed, if the charged particle projected into the magnetic field, it will follow a circular path. it will follow a circular path. It will move like this. Again, if you provide the same window here, if you provide same window here, then the charge particle will not pass through the window but will strike on this wall. Okay? So then how to allow the charge particle to move through the window? Now we will combine the electric field and magnetic field. Combine the electric field and magnetic field. See, I am representing first the electric field. Combine the electric field and magnetic field. I am representing first electric field. Electric field directed in upward. This is direction of electric field, and here also in the same space there is a uniform magnetic field in outward direction. What we have discussed, you may take inward direction also. Magnetic field, uniform magnetic field, and magnetic field is B. Electric field is E. Okay. This is the window from our discussion. This is the window. In both cases, the charge particles are not passed through the window because this is a parabolic path and this will complete a circular path. This will complete a circular path. If the obstruction is removed, then it will complete a circular path if magnetic field is filled in the space. Okay. Now we have represented both electric and magnetic field. Now the same entrance is provided. This is entrance. This is entrance, and a number of charge particles are allowed to flow to the combined electric and magnetic field. See, as we have discussed, if a charge particle moves in a space where both electric and magnetic field are present, then the resultant force is called as the Lorentz force. Okay, and in this case, the resultant force is force due to electric field is QE, force due to magnetic field is Q in V cross B. Okay. So we have observed the effect of electric field and effect of magnetic field, and now this is our window. This is our window, a small opening here. This is window. Let a positively charged particle plus Q enters into the field like this V. Then see, velocity of charge particle is perpendicular to both electric and magnetic field. See, electric field is in upward direction and velocity is in, suppose electric field is along y-axis and velocity is along x-axis. So angle between velocity and electric field is 90 degree, and also magnetic field is directed outward field, that field. So again, angle between velocity and magnetic field is 90 degree. Okay. So due to electric field, the charge particle will experience a force and will tend to move in a parabolic path, and due to presence of magnetic field, it will tend to move in a circular path. Okay, but we need the charge particle should pass straight through the window. Means the charge particle will not get deviated. As we have projected, it will pass straight through the window. Then what we have to do? See, So this is direction of magnetic force due to magnetic field, and this is force due to electric field. See, on this charge particle, in upward direction, force is electric force, that's equals to QE, and in downward direction, that is magnetic force. And here in this case, magnitude of magnetic force is QV. So, due to presence of both electric and magnetic field, the charged particle experiences force due to electric field and force due to magnetic field. Then how the charged particle will move straight? Means how the charged particle will move undeviated? Means to move the charged particle undeviated means to pass through the window. Resultant force on the charged particle should be zero. Resultant force on the charged particle should be zero. So, resultant force is the Lorentz force. Lorentz force means combined force due to electric field and magnetic field should be zero. So, that's equals to QE plus Q in V cross V. You see, then QE is equal to minus into Q into V cross V. The negative sign implies that the forces are opposite. The forces are opposite, and here if you take magnitude is QV and magnitude is QV. Okay, and to pass the charged particle undeviated, Q get cancelled, and this shows velocity of charged particle is equal to E by V. Velocity of charged particle is E by V. So, if this condition is satisfied, we have taken resultant force. To have zero resultant force, this condition should be satisfied. Means magnitude of velocity should be equals to ratio of magnitude of electric field to magnetic field. Okay, magnitude of electric field divided by magnitude of magnetic field, that's equals to magnitude of velocity. If this condition is satisfied, then the charged particle will move straight, means undeviated. Clear? Okay. So, if a number of charged particles are moving with different velocities, so let's take velocity of this particle is V1. Okay. Another charged particle, suppose this is Q1, another charged particle is Q2, this is projected with a velocity V2, another charged particle Q3, this is projected with velocity V3. So, there are different velocities V1, V2, V3, V4 up to Vn. Suppose you want to allow only this charged particle which has velocity V1, then in this case V1 is equal to, should be equals to, V1 should be equals to E by V. So, thus velocity filter allows those charges only if this condition is satisfied. So, from a number of charged particles, those particles will pass through the window which have velocity V1, means ratio of magnitude of electric field to magnetic field. Okay. So, velocity filter is also called as velocity selector, or this is called as Wien filter. Okay. A small discussion, short discussion, and I hope you have enjoyed the class. Thanks, my children. In next lecture, we'll again discuss a beautiful concept on same theory, force experienced by charged particle. Okay, thanks.